Welcome to Innovation Pulse, your quick, no-nonsense update on the latest in AI. First, we will cover the latest news. OpenAI's o3 and o4-mini models redefine visual intelligence. Anthropic's Claude AI now integrates with Google Workspace. Google's Gemini Flash model offers enhanced efficiency, and xAI's Grok Studio boosts collaborative project creation. After this, we will dive deep into the innovative role of AI in creating images, videos, and sounds using advanced latent representations. Stay tuned. OpenAI's latest visual reasoning models, o3 and o4-mini, represent a major leap forward in visual perception by integrating image-based reasoning into their thought processes. Unlike previous models, these can manipulate images, cropping, zooming, and rotating them to extract insights, allowing for more thorough and accurate problem-solving. For instance, users can upload images of complex problems, like an economic set or a code error, and receive detailed analyses and solutions. These models excel in multimodal reasoning, achieving top marks in STEM and visual tasks. However, they still face challenges like overly long reasoning chains and occasional perception errors. Despite these, o3 and o4-mini greatly enhance visual intelligence, setting new standards in the field. OpenAI continues to refine these capabilities for more efficient and reliable use, aiming to improve multimodal reasoning for everyday applications. Anthropic recently upgraded its Claude AI assistant, introducing autonomous research and Google Workspace integration, making it a true virtual collaborator for enterprise users. Claude's new capabilities allow it to conduct independent research, providing answers in minutes, unlike some competitors that take up to 30 minutes. This speed is crucial for busy executives needing quick responses for time-sensitive decisions. The integration with Google Workspace connects Claude to users' emails, calendars, and documents, streamlining workflows. Emphasizing security, Anthropic ensures that data is protected and not used for training models. Claude addresses AI's tendency to produce incorrect information by citing sources, building trust in business-critical applications. Early users report significant time savings. As AI tools evolve into proactive research partners, Anthropic's focus on speed and enterprise needs positions Claude as a strong competitor in the AI productivity market. Join us as we step into the future of AI innovation. Google's latest AI model, Gemini 2.5 Flash, is now available as a preview in the Gemini app. This model aims to enhance performance over its predecessor, the 2.0 Flash, and is designed to be smaller yet more efficient. Google has introduced new API pricing for developers, which is lower than competitors, allowing them to integrate the model into their applications. This version supports Google's Canvas feature for text and code work and includes built-in simulated reasoning, known as thinking, to improve output accuracy. However, thinking can slow responses and increase costs, so developers can adjust these settings to suit their needs. Google's Director of Product Management for Gemini, Tulsi Doshi, emphasizes that feedback from this preview will guide future improvements. The ultimate goal is to offer a simpler yet flexible experience for both developers and consumers. Elon Musk's AI company, xAI, has introduced Grok Studio, a new feature for their chatbot, Grok. Announced on X, Grok Studio allows users to edit and create documents and basic apps. It's available to both free and paying users on Grok.com. Grok can now generate documents, code, reports, and browser games. The feature opens content in a separate window, enabling collaborative work. Grok Studio includes code execution and supports Google Drive, allowing users to attach files to prompts. It supports programming languages like Python, C++, and JavaScript, offering a dedicated workspace similar to OpenAI's Canvas for ChatGPT and Anthropic's artifacts for Claude. Grok Studio's integration with Google Drive enhances its utility, enabling work with documents, spreadsheets, and slides, making it a versatile tool for software and writing projects. OpenAI's new models, o3 and o4-mini, are released with enhanced reasoning capabilities and access to tools like web browsing and coding. These models represent a step forward, combining simulated reasoning with features like visual analysis and image generation. They offer significant improvements over previous versions, such as better accuracy in programming and business consulting tasks, and improved cost efficiency. The o3 model is noted for its near-genius level in generating insightful scientific hypotheses. However, OpenAI's naming conventions can be confusing, as o3 is more powerful than o4-mini. The models are available to ChatGPT Plus, Pro, and Team users, with broader access rolling out soon. Additionally, OpenAI introduced Codex CLI, a terminal-based coding tool, alongside a grant program to encourage its use. Despite promising early feedback, independent verification of the model's benchmarks is advised. And now, pivot our discussion towards the main AI topic. Today, we're going to explore how modern AI creates images, videos, and sounds. Most people think these systems work directly with pixels or sound waves, but they actually use a clever two-stage approach. Joining us is AI researcher Yakov Lasker to break down how this works in simple terms. Welcome, Yakov.
Thanks for having me, Thomas. This is definitely a fascinating area that doesn't have to be overly complicated to understand. I'm ready for your first question.
Let's start with the basics. In simple terms, what does it mean when we talk about latent representations in generative AI?
Think of latent representations like a compression system. When you zip a large file on your computer, you're creating a more compact version that contains the essential information. In AI, latent representations work similarly. They're compressed versions of images, videos, or sounds that contain the important parts while filtering out unnecessary details. For example, if you have a photo of a cat, the AI doesn't need to remember every single pixel. It can create a compact representation that captures the cat's shape, color, and position, while ignoring tiny details that wouldn't be noticeable to most people.
So why do AI systems use this two-stage approach rather than working directly with the original images or sounds?
It comes down to efficiency and focus. Imagine trying to paint a landscape by placing one grain of sand at a time versus using broader brush strokes. Working directly with pixels or sound samples is like placing individual grains. It's inefficient, and you spend too much effort on details that don't matter. The two-stage approach lets AI systems focus on what's actually important. First, they compress the input into these more meaningful representations. Then they learn to generate new versions of those representations. It's much faster and requires less computing power, which means cheaper and more accessible AI for everyone.
Could you walk us through the basic recipe for how these systems are built?
Sure, the recipe has two main stages. In the first stage, we train what's called an autoencoder. Think of it as a compression-decompression system. One part, the encoder, turns images into compact representations, and another part, the decoder, turns those representations back into images. In the second stage, we train a generative model that learns patterns in these compact representations. When we want to create something new, this model generates a new representation, and then we use the decoder from the first stage to turn it into a final image, video, or sound. It's like first learning to write music notes, then composing a new song, and finally playing that song on instruments.
That's helpful. How do these systems know what details are important to keep and what can be thrown away?
They learn this through a clever combination of different training goals. One goal forces the system to recreate the original input as closely as possible. Another goal, called a perceptual loss, ensures the reconstruction looks good to human eyes by focusing on features we notice. A third goal, the adversarial loss, uses another AI that tries to spot fake images, pushing the system to create more realistic outputs. It's like having three different critics when learning to cook. One measures if you used exactly the right ingredients, another checks if the flavors work well together, and a third determines if the dish looks appetizing. Together, they help the AI understand what matters to humans when looking at images or listening to sounds.
You mentioned efficiency earlier. How much more efficient is this two-stage approach?
The difference is dramatic. A high-resolution image might contain millions of pixels, but its latent representation might be 10 to 100 times smaller. For video, the difference is even greater. This means AI systems can generate content much faster using less computing power. What might take hours on a powerful computer can be done in minutes or seconds. It's like the difference between sending a full-length movie versus sending a short summary with key scenes. Both tell the story, but one requires much less bandwidth.
How does this relate to how humans perceive the world around us?
That's a great question. Our approach actually mirrors how human perception works. When you look at a grassy field, you don't process each blade of grass individually. You perceive grass texture. Your brain abstracts away the details and focuses on the meaningful patterns. These AI systems do something similar. They learn to represent areas like grass or sky as patterns or textures, rather than individual pixels. This is why these systems work so well. They're designed to match how our brains already process visual and audio information, focusing on what's perceptually important rather than raw data.
What are some of the challenges in designing these latent spaces?
One big challenge is finding the right balance between compression and quality. Compress too much, and you lose important details. Compress too little, and you don't get the efficiency benefits. Another challenge is what I call the tyranny of the grid. Digital images and videos are organized in grids of pixels, and we typically keep that grid structure in the compressed representation. But information isn't distributed evenly across an image. A person's face contains more important details than a plain blue sky. Yet, our grid structure allocates the same resources to both areas, which is inefficient. There's also the challenge of making sure these compact representations remain modelable, meaning they still have enough structure for the AI to learn from them effectively.
Are there differences in how this works for different types of content, like images versus audio or video?
Yes, absolutely. For images, we've developed a pretty mature understanding of what matters perceptually and how to create good latent representations. For video, we add a time dimension, which complicates things because we need to account for motion and consistency between frames. Audio presents its own challenges because human hearing works differently than vision. What's perceptually important in sound relates to things like tone, pitch, and timing, rather than spatial patterns. Language is actually the most different. Since human language evolved for efficient communication, it doesn't have nearly as much redundancy as images or sounds. You can compress an image to 1% of its original size and still recognize what's in it. But if you removed 99% of the words in a book, you'd lose the meaning entirely.
How does this technology relate to the AI image generators that have become popular recently?
Popular systems like DALL-E, Midjourney, and Stable Diffusion all use this two-stage approach. When you type a text prompt and get an image, the AI is actually generating a latent representation first, then decoding it into the final image you see. In fact, Stable Diffusion is explicitly named after its approach. It uses a diffusion model that operates in a latent space. This is why these systems can generate images so quickly compared to earlier technologies. They're working with these representations rather than generating every pixel directly. The text prompt helps guide the creation of these latent representations, focusing on the concepts you've described, but the actual generation happens in this compressed space before being expanded into the final image.
How might this technology continue to improve in the future?
There are several exciting directions. One is making these latent representations even more efficient by moving beyond rigid grid structures to more flexible approaches that adapt to the content. Another promising area is improving how we handle video and audio, where our current approaches aren't as refined as they are for images. We're seeing research on better ways to capture motion and temporal relationships in these compressed representations. We'll also likely see more end-to-end approaches as computing power increases. Right now, the two-stage approach makes economic sense because it's so much more efficient, but eventually we might reach a point where the simplicity of a single-stage approach outweighs the efficiency benefits.
What does all this mean for everyday people using AI tools?
For everyday users, these technical improvements translate to more impressive capabilities in the tools they use. Better latent representations mean higher quality outputs, faster generation times, and more affordable AI services. It also means AI will be able to generate longer videos, higher resolution images, and better quality audio without requiring supercomputers. The apps on your phone will be able to do things that once required specialized hardware. And as researchers develop more semantic latent spaces, ones that capture meaning rather than just appearances, we'll get better control over generation. You'll be able to edit and refine AI-generated content more intuitively, specifying exactly what you want changed without affecting other elements.
For someone interested in this field, but without a technical background, what's one key concept you'd want them to understand?
I'd want people to understand that these systems aren't magical. They're essentially sophisticated compression tools paired with pattern recognition engines. They work by focusing on what matters perceptually to humans and ignoring the rest. This explains both their strengths and limitations. They excel at creating content that looks or sounds good to us because they're designed around human perception. But they don't truly understand the content the way we do. They've just learned patterns in the data. Understanding this helps set realistic expectations about what these systems can do well, create visually appealing content, versus what they struggle with, ensuring logical consistency or factual accuracy in that content.
This has been a fascinating and accessible explanation of a complex topic. Thank you, Yakov, for helping us understand how modern AI creates the images, videos, and sounds we're increasingly seeing everywhere.
It's been my pleasure, Thomas. These technologies can seem mysterious, but the core ideas are actually quite intuitive once you strip away the technical jargon. I'm excited to see how they continue to develop and how people will use these tools in creative and productive ways.
That's a wrap for today's podcast, where we explored the advancements in AI with OpenAI's visual reasoning models, Anthropic's enhanced Claude AI, Google's Gemini Flash model preview, and xAI's Grok Studio, alongside a discussion on how modern AI systems efficiently generate multimedia content using latent representations. Don't forget to like, subscribe, and share this episode with your friends and colleagues, so they can also stay updated on the latest news and gain powerful insights. Stay tuned for more updates